Hey there! Let's dive right into turbine conversion to hydrogen fuel. By switching turbines to run on hydrogen, we can make energy generation far more eco-friendly, especially if we use green hydrogen, which only releases water vapor as a byproduct. But it's not just about swapping fuels. It requires a complete overhaul of infrastructure, from engine redesigns to updated fuel systems. Let's explore. First thing, we need to adjust the turbine's combustion system. This is crucial because the way hydrogen burns is fundamentally different from natural gas. Hydrogen has unique properties that require special handling. One of the main differences is that hydrogen is a much smaller solar molecule compared to methane, which makes it more prone to leakage when used in infrastructure designed for natural gas, such as existing piping and fittings. This means that systems transporting hydrogen require reliable leakage detection. Hydrogen's energy density by volume is much lower, requiring larger storage and modifications in fuel handling. Hydrogen needs more air for complete combustion, affecting turbine air handling requirements. Hydrogen's lower density results in a lower volumetric energy content, requiring larger fuel volumes to be supplied. In practical terms, this means that to achieve the same energy output, significantly more volume of hydrogen is required. There are combustion challenges. Hydrogen combustion produces higher NOx levels, requiring advanced control strategies. Dry low NOx (DLN) combustion technology helps reduce these emissions through lean premixed combustion. Converting gas turbines to run on hydrogen demands substantial modifications due to hydrogen's high flame speed, low ignition energy, and higher flame temperatures. Changes include redesigning the burner and fuel injectors, adjusting the fuel-air ratio, employing advanced cooling techniques, upgrading materials, enhancing control systems, and improving safety measures for hydrogen's flammability risks. Since hydrogen is more reactive than natural gas and has a much higher flame velocity, this reactivity can lead to combustion challenges such as flashback and flame holding. Flashback occurs when the flame propagates back towards the fuel source, while flame holding refers to the flame attaching to the fuel supply point. Both situations can cause severe damage to turbine hardware. To address these issues, modifications are required to the startup and shutdown sequence, as well as the control systems, to ensure stable operation. Hydrogen combustion generates higher flame temperatures, which can lead to thermal stress on turbine components. Advanced cooling methods for turbine blades and other hot sections are needed to handle increased thermal loads. Turbine materials used in GTs must withstand increased temperatures and potential hydrogen embrittlement. Therefore, alloy composition and protective coatings need upgrades. Converting an existing power plant to run on hydrogen requires several modifications. Install an electrolyzer system if the plant intends to generate its own hydrogen from water using excess renewable electricity. This will also require a dedicated water source. The energy required for this is approximately 39.4 kilowatt hour per kilogram of hydrogen produced. Hydrogen storage tanks need to be integrated on site. The storage system can be either pressurized gas tanks or cryogenic tanks, depending on the hydrogen state. Safety measures must be upgraded to include hydrogen sensors, flame detectors, and other leak detection systems, because hydrogen is more flammable and disperses quickly. A hydrogen-compatible fuel delivery system, including new fuel lines and compressors, is necessary. The current natural gas pipelines cannot be used due to hydrogen embrittlement risks. Cryogenic technology for hydrogen transport involves cooling hydrogen to negative 253 degrees centigrade to transform it into a liquid. This process significantly increases the volumetric energy density, making it ideal for bulk transport and storage. However, challenges include the high energy requirements for liquefaction, boil-off losses, material compatibility, and the need for strict safety measures. Despite these challenges, liquid hydrogen plays a crucial role in long-distance hydrogen transportation. Siemens, GE, and Mitsubishi Power are all committed to transitioning their gas turbines to operate on hydrogen, either as a blend with natural gas or on 100% hydrogen in the future. Currently, most turbines can handle hydrogen blends between 30% and 75%, with significant ongoing R&D to push towards full hydrogen capability. Hydrogen-compatible and hydrogen-ready turbines are likely to play a significant role in decarbonizing power generation, especially as hydrogen production costs decline and hydrogen infrastructure scales up globally. Running gas turbines on hydrogen offers significant benefits, especially for industries needing low emission, high efficiency power. Refineries, which produce hydrogen as a byproduct, are ideal candidates for this transition. Hydrogen-powered GTs can be integrated with combined heat and power systems, providing both electricity and steam for refinery processes. Industries like ammonia production, renewable energy plants, steel production, remote locations, and data centers can also benefit from hydrogen GTs. Hydrogen helps balance renewable energy, supports green steel production, and offers an eco-friendly alternative for off-grid power. While hydrogen remains more expensive than natural gas, industries with access to affordable hydrogen stand to gain the most. As technology continues to advance, hydrogen turbines will become even more efficient and affordable. This will accelerate their adoption and pave the way for a greener and more sustainable future. The journey towards a hydrogen-powered future is just beginning, and it's going to be an exciting ride.